Good afternoon and welcome to Operations 1. Just a reminder for all delegates while you are in the venue and walking around the venue to ensure that you've got your badge around your neck. It needs to be on at all times. For this session, we've got three speakers. First up will be Massimo from NTT to speak about geolocation and hopefully solving everyone's problems of being VPN to the wrong country every time you want to use Netflix or something else. So, Massimo, please come up.
Thank you very much. Hello. So, good afternoon. Good afternoon, everybody. So, my name is Massimo Candela. I'm a principal engineer at the Global IP Network of NTT. And today I will tell you how you can easily and reliably fix your geolocation issues. So, imagine you have a customer that it's calling you and it tells you, oh, this website is geolocating me in this country, but I'm in the other country. You can, with this system, without contacting anybody else, by yourself, fix it essentially just by editing a file, okay? And this is also thanks to this RFC 1992. Hey, there we go, this RFC 1992, which I'm proud to say that in 2.5 years, more or less, it got a great adoption. And this is what makes this working reliably. In the audience somewhere, which I don't see, maybe in another room, there should be also Randy, which is one of the co-authors of this RFC. But he probably knows already everything about it, so it's not. So let's go. So what are we talking about? So the process of IP geolocation is essentially, from an IP, you want to know the geolocation of it, so the country where it is connected. And this is done millions of times per day, and the reasons are various. It can be because of you have to respect country regulation, provide localized content to your users, optimize latencies, troubleshooting research. It doesn't matter why you do it, but it is a common thing that is done. Now, what is the problem of this? The problem is that this IP geolocation thing started in an uncoordinated way. So where is this data coming from? So there is no central repo that you can identify. So the RIRs are not geolocation providers, and they don't want to be geolocation providers. We don't want them to do the role of geolocation providers, but still they have some geolocation hints coming from WIS. Then there are the real geolocation providers. They offer a service, so basically from IP to location, and there are many geolocation providers, and so several data sets. And finally, there are the content providers. The content providers, they use the geolocation services offered by the geolocation providers, but they also want to fix things on fly, so they basically fork and patch this data set, so they have their own copy of this data set. This means that when something is wrong, where is this data? There are various data sets. It's difficult to pinpoint where. Also, there is not a strategy to derive geolocation. So there is not a formula. It's mostly guesswork done by geolocation provider, good work, but still guesswork. So it's based on WIS, reverse DNS, latencies, the more advanced one. But still, since there is no process, there is also no way for you to actually tap into the process and fix it. And finally, basically, all of this, there is data that is about the location of your resources, and you didn't have any say in this. And so basically, you cannot, you don't know where it is, you didn't provide this information, and you don't know how to fix it. So how does it work when it's wrong? When it's wrong, usually what you do is you contact, you basically try to change stuff in WIS. You contact the various you broadcast an email to all the geolocation providers. That's mostly how it used to work. And in NTT, at some point, I started receiving requests. Oh, how do we fix the geolocation of this customer? How do we fix the geolocation of this? Or, and again, oh, it didn't work, so what do we do now? And at some point, I said, okay. First of all, I don't have an answer. But even more importantly, how many of these emails are we sending per month? It clearly is a broken process. So I said WHOIS has some hints. WHOIS is actually quite heavily used by geolocation providers to derive geolocation. And this is one of the questions. So what about WHOIS data? Yes, what about it? So there are two attributes. There is the geoloc attribute and the country attribute. The geoloc attribute is supported by 2 out of the 5 regional internet registers. And this already is a problem, because a solution that works only in part is already a weak solution that is not going to be reliably used. The second problem is it allows to use latitude and longitude, which is the really specific geolocation format, and it's also really not human-friendly. And you associate this latitude and longitude to entire INNAM, which can instead span across different even continents. And what if you want to geolocate, I don't know, more specifics or even single IPs? Are we going to create a bunch of INNAM in WHOIS and basically overload the data set? Then there is the country attribute. The country attribute is actually an attribute supported by 3 out of 5 RIRs. It is better because it's an ISO code, 2 letters, so much easier to use. There is no granularity, so you cannot specify a city, but okay, that's fine. 3 out of 5 RIRs, so it's a bit better, but still, the 3 RIRs, they all have a different definition of what this attribute is. AppNix says country is the country where the INNAM, where the network is deployed. Perfect. This is the wisest definition, in my opinion. Then there is LACNIC. LACNIC says, no, this is the country of the organization that is the resource holder, so that owns the prefix. And then there is RIPE that says, hold my beer. And basically, in the documentation you can read, it has never been specified what this country represents. It could be the location of the head office of a multinational company, or where the service center is based, or the home of the end user. So essentially, there is a country attribute, which is mandatory, which by definition has, you put a country. Of course, you can see that this is not a reliable way of proceeding. And by the way, all of this, they have, in my opinion, even a biggest flaw, the fact that they are directly coded in WHOIS. Not only they don't scale because you have to create INNAMs, but in organizations, for example, like NTT, not everybody, not all the network engineers have access to the RIR portal, and they can just go every time to change whatever they want. And so basically, the people that they know where the geolocation is, they are not the one that they can update this data. They have to ask somebody else, and this is a recipe for stale data. So, solution. So, RFC 1992, we wanted to do something, it's really simple. We wanted to do something based on things that they already existed, nothing new. So, we take a file, which is the geofit file, a format that already existed, used heavily by geolocation providers and by operators. And this file describes geolocation corrections, and it was usually shared by emails. And we remove the emails part. And basically we say, okay, we take this format that you already know, so it's already in your pipelines, and we link it from WHOIS, essentially. It's simple as that. And we do that by using initially remarks, we will see. And the reason for that is that so the RIRs, they don't have to necessarily implement anything. We already use something that is implemented by everybody. So the solution is already there. We just combine together. More importantly, we actually specify how this data can be safely parsed and safely used. Because if I send you a geofit file by email, and I tell you this prefix has to be here, you are a geolocation provider, you receive this email, how are you going to? First of all, know that I am who I say I am, that I work for the company I say I work, that the company owns the prefix, and that I am authorized to change the geolocation there. And then I raised these questions, and I got no answers or really weird answers, like, oh, we checked the domain of the email. What does it mean? And or like we look in WHOIS manually, but how do you really validate this entire thing? You're just receiving a file on an email. So we provide a way to validate this, but also there is also an optional signature if you really are keen on make it even extra safe. So let's just start doing it. How does it work? Basically, you create a text file, a CSV file, okay? The CSV file is simple. Each row is a geolocation for a prefix. You put a prefix, comma, a country code, comma, a region code, comma, a city, comma, nothing. You can put a zip code, but it's basically deprecated. Why would you go in that detail? So there is a trailing comma in the end. When I say country code, region code, I'm talking about ISO codes. Please do not invent them. They are already available. I see a lot of geofeeds file they have some arbitrary, so you can search on or Google whatever you want, or you can go in the ISO code database. They are easy to find, and they are all optional. So you don't have to place all of them. You can also just place the country. You can place the country and the city if it's not ambiguous, or you can even don't place anything and just do comma, 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 which means I don't want to be geolocated. It's a wish. It's not necessary. You're going to be respected, but that's what you can do. Then you take this file, you publish over somewhere, hosted on HTTPS, and then you add a remark. You find the INNAM that encompasses the resources that you want to geolocate, and you add a remark that has, the remark is a text field, essentially. In RN is even called comment. You can put whatever you want. That's why it's already implemented across all the Fiverr IR. And you put this type of comment, which is like a geofeed with the uppercase G and a URL. If you are in RIPE and AppNic, they implemented a specific attribute called geofeed, so it's even better. You can use that attribute. Now, what you basically did is that you created a file that you can manage. You ask your director or whoever has access to link it once. From that moment on, you can edit that file yourself, and you don't have to share it with anybody because the geolocation providers are automatically going to fetch this. They are going to be able to find it from WHOIS data. So this is an example of the file with all the prefixes and the various possible geolocation that you want to use. This is something part of our identity. This is an example of what you would do if you would add a remark. This, in case, is an example with entity, with RIPE, and you see it's just a string geofeed and the CSV file. But again, AppNic, this is how you would do in AppNic. This is a screenshot of your RIR portal, and look what they did. They have a geofeed attribute. So you just put a clean, nice URL. And I have to say, they did a great work. It's also, I think, the best implementation so far of this, of the geofeed attribute, and so fast. This is what you would see if you go in WHOIS. Basically, why WHOIS anyway? Because that's where, even if you cannot have write access, that's the place where everybody goes when he wants to know something about a prefix or an IP. So it's the authoritative source. He has to start from there. And he also allows us to verify ownership. So this is it. This part is extremely important. Please do not forget this. Every entry that you have in the geofeed file is validated, is accepted only if there is an encompassing INNAM in WHOIS that refers to the file. So we start from here, and we read in the file all the prefixes and IPs that they are inside this INNAM. You can put a file with multiple prefixes, even of different disjoint prefixes, INNAMs. That's fine, as long as you have another INNAM pointing to the same file, for example. So if you forget to put a link in this one, 45.1/20, this IP here is going to be ignored because it's not linked by anything which we cannot verify that you actually own it, and it's just going to be lost. So remember to put a INNAM reference to an encompassing INNAM. So adoption numbers, let's quickly see the adoption. So I'm really proud to say great adoption. There is this website, geolocatematch.com, which there is an experiment running constantly that tracks adoption numbers. automatically. And we have more than 200,000 prefixes already with geofeeds. It's 2 years for an RFC is relatively recent. More than 200,000 prefixes, and but even more importantly, we have a list of all the geolocation providers that actually implemented that. It didn't come for free, a lot of talking with them. But they implement that, and they are basically, I mean, all of them, or at least all the most important, including there is Maxmine here. And there is a column here where you can see the frequency, most of which have, you see, for example, 1 day, which means that if you create this file and you put your geolocation in 1 day, they are going to be able to auto-discover them, fetch the content, and fix it without you sending them any email. In the same web page, you can do a test. After you install your geofeed, you can put your INNAM or anyway a prefix, and you can check. He's going to download the file, check that everything is correct, also the country codes and everything, and everything is green. You are good to go. You have also some FAQ if you want more information, and there is also this file at the bottom where I, every day, collect all the geofeeds across all the 5 RIR, compile a single file, and basically this is if you want to use them to get information about other operators' geolocation. Now, a bit of statistics. RIPE and ARIN have by far the most number of prefixes with geofeeds at the moment. And APNIC has only 2.7% more or less, and I mean, and APNIC is also the one that better and sooner deployed a geofeed attribute, so they did a great effort for you use it. Also because the region has possibly more than the ARIN and RIPE region has geolocation issues. So this is the way how you could fix this. So a bit of extra. Imagine that you didn't understand anything of what I said. Don't worry. There is a tool for it. You can just follow. It's something even a kid can do. You can just follow this wizard. You can find it in packetvis.com/geofeed. This is not an NTT service. And, or you just go on the Packetvis website, there is an icon, geofeed. Basically, just follow the wizard. It says, give me the prefix that you want to geolocate or the IP. The next step is, well, tell me where it is. You can search in the form, and it even gives you a map. And it's just going to take all the ISO codes for you, so that you don't have even to worry about the ISO codes. They are going to be good. And then it tells you, okay, then now go in WIS and in this INNAM and put this remark or this comment, depending on the RIR. It even tells you there is a link here at the top that says, oh, this is where you have to go. So basically, if you click there, it brings you directly on the page to edit the INNAM for your RIR, and you have to just log in and follow the instruction to add what it says. So this tool creates the geofeed file and hosts the geofeed file for you over HTTPS, so you can really copy and paste this, and it just works. It's hosted for you, but if you want to host it yourself, you just switch this, and basically you put your URL. Is the same process. Is going to tell you, okay, just it's just going to change the URL, but the instructions are the same. Then you test, and it's going to tell you, well, it's green, everything is good, nothing else to do. Your geolocation is going to be updated. There is an extra feature here, this button here, if you care. I find it quite nice. That is basically, it's going to give you, if you click there, it's going to do a test across all the geolocation providers. It's going to give you a list of all the geolocation providers, and it's going to check that prefix, where they say it is. And basically, once, and basically you will see, okay, they say it's here, 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 and maybe you check 1 day later, and some of them, they already synchronized with what you said in the geofeed. 5 days later, maybe they are all synchronized, and you fix your problem. Well, basically that's it, and just a quick recap, a few URL for your convenience. This is a summary. Basically, the first one is the tool to do the setup. The second one is to track adoption and to also test. The third one is an open source project that is, if you are on the other side, if you are in the business of fetching this data, not providing, but fetching, basically you run it and it's going to fetch and validate automatically across all the 5 RIRs. This is what currently many geolocation providers are using to adopt this system. And there is also the link to the RFC. I think we have some time left, so thank you very much for your attention. And if you have questions, we can do them now. I don't know if we have time or what, just let me know. Thank you.
Thank you, Massimo. We've got time for a few questions, if anyone. Yep. If you can just state your name and your affiliation.
Arne Nipperdikix. Is there any recommendation? Should you put the geolocation data in one file, or especially if you have a lot of prefixes or INetNum, it may take a while to go through this file and find the right INetNum, or to split them?
Thank you for the question. That's a good question. So the most convenient way, the easiest way, is to create one file and host it somewhere and link your INetNum to the same file. It's easy so that. However, there is a catch. So as I show you in this slide, you basically can have how many INetNums you want pointing to the same file, as long as you link all of the, you take the less specific that you have, you link it from that moment on, you can specify in the file whatever more specific you want. And that's fine, you can link all of them to the same file. If, however, there is an extra safety feature that in case you will need it, that is optional, which is using basically your RPKI certificate to sign the file. If you do that, you have to split different files, because of course each certificate validates only a specific set of resources. So if you don't sign it and you basically the validation that you trust is the one done by following the INetNums of the RIRs, which is at the moment I think 99% of the geofeeds producers, one file is enough. I hope I answer. Perfect. Any other question?
There's just a question on Zoom from Bayer from APNIC. He's asking if there are any differences in creating a geofeed URL for IPv6 addresses.
No, it's exactly the same. Well, maybe I should have done an example with IPv6, but sorry for that. But yeah, it's exactly the same. Maybe I have it in the file. Wow, not even in this. Okay, no, yes, it's exactly the same. Just put an IPv6 in the file, prefix or IP, and it's exactly the same. You go in WIS, you put the link, and nothing changes. Any other question? Okay.
Maybe one from me.
Okay.
I know that some of the geodatabases have different prefix acceptance sizes, so they may accept maybe up to a /30 rather than a /32 or so on. MaxMind, I think, only go up to a 64 for IPv6. Is there any plan maybe for that tool to start doing additional validation? So you've got your geofeed published, you've got the prefix, it's matching in INetNum, but now how does it look in some of the popular geodatabases?
So you're asking if there is a way to fetch if they actually got the information?
If they've got the information, and then how have they processed it?
Yeah, so this. You go to this tool. Ooh, okay, where's the last line? No, this tool, and you click on this button here, and it gives you a list of all the geolocation providers, and it tells you where they actually located it. And if you, I don't know, a month passes and you see that it's not yet fixed according to your geofeed, and basically you can complain with them, or there is also a feature where packet is sent email to them. But yeah, in general, that's the way. Or you can go on their website and check yourself.
Awesome. All right.
Perfect.
Anurag?
We have time, right?
Yes.
Anurag Bhatia, Hurricane Electric. Just curious, how do people publish the feed if they are using massive CGNet? And have their IP spread across multiple cities, states?
So you're saying something like in case of Anycast or something
No,
like
no, CGNet. So having a gateway somewhere, CGNet gateway in city 1, and that IP is being shared across whatever, 5, 6 cities. So what's the best practice in such things?
So at the moment there is no, this is not, so for any case in which an IP address or a prefix has multiple locations, this is not the way to address it. There is no case for that, but also in general, geolocation providers, they do not treat that case. So it is like they want to know from an IP a single location. So they also, most of them, at least, they don't support multiple locations.
Okay, thank you.
Which is also, by the way, I would say that not the main use case how this type of data is in general used. That is more related to, for example, content provider to understand where customers are. Perfect.
Okay, thank you, Massimo.
Thank you very much.
Okay, next up, we have a tag team, actually. So we will have Richard first up, and then Shane, both from Searchlight New Zealand, NZ, to talk about their OpenLI project and updates around mobile. Thank you.
If we go a few minutes long, is that okay? Because we started it. Hopefully it works. Right, so as we just said, this is a two-part presentation. I'm going to introduce the concepts and the project and talk about why we're doing what we're doing. And Shane is going to talk about the technical details of what we are actually doing. So, lawful interception, it's a bit of a niche subject. It doesn't impact anybody's customer services, or shouldn't impact anybody's customer services or their financial performance. So people try and ignore it if they can. So we better start at the beginning and talk about what it actually is. This is the ETSI definition of it. We'll talk about ETSI a bit more in a minute. It gets the legally sanctioned bit right, okay? There's always some sort of law that enables you to do this, and the law enforcement agency will provide a warrant to say that this is a legal process, and the network operator has to do something. So that part of the law is it requires the network operator to do something normally. Unfortunately, this definition defines interception as, well, interception, which is, you know, a problem because interception means things like commandeered or seized, which is not really right. It's closer to the sort of traditional idea of wiretapping. Obviously, these days, there's not really wires involved very often. And in a network sense, it's probably mirroring and filtering. But the network operator intercepts the communications and passes the contents back to the law enforcement agency. And the key thing about it is it's really a tool to assist the law enforcement agency, the police or security agency, in investigation of major crime, right? They have to put resources in, so it's dealing with things like murders, drug rings, organised crime. In pictorial form, it looks like this. We've got a police officer on the right-hand side, and he will send a warrant or a court order to the network operator, which might be somebody in this room. The network operator will configure their lawful interception system, and the lawful interception system will take the traffic from the network, it'll sequence it and encode it, and sends it securely back to the law enforcement agency. In particular, normally it will send not only the contents of the communications that's been intercepted, but a metadata around it, particularly signaling data that's involved. The process of adopting LI in a jurisdiction, a country, goes like this. It always starts with the law, right? Lawful interception, you've got to have a law. Laws are typically quite general and difficult to change. So normally there's some sort of regulations that come afterwards that specify how it's going to be done and where the handovers are, things like that. After that, the law enforcement agency has to implement their side, because there's no point in the operator doing anything if the law enforcement agency can't receive the data. And then the operator will do their stuff, and you have a working LI in system process in a jurisdiction. This is just an example. It's the example we're most familiar with because we're from New Zealand. So the current law is the piece of legislation affectionately known as TICSA that was replaced the previous law in 2013. Half of it deals with interception and half of it deals with network security. And then 4 years later, they introduced a set of regulations and published them in the New Zealand Gazette. And the regulations said that everybody had to use the ETSI standards. So ETSI is the European Telecommunications Standards Institute. It's the most widely used set of standards. Apart from a couple of big countries like the USA that have their own domestic standards, almost everybody else in the world that has a mandated LI system has adopted the ETSI standards. The big advantages from the law enforcement side is that it's real time. So the police can listen as the criminals are making a telephone conversation and organising a drugs deal or whatever it is that they might be doing. Another big advantage is that the combination of collecting the signalling and the defined encapsulation form forms a chain of evidence that's been tested in court, so it can be used for prosecutions. The final advantage, which is not on this slide, is because everybody uses it, there are lots of systems available, so you know, it's well supported. And in particular, there is even an open source implementation, which is where we come in. So our project is called OpenLI, and we claim, and nobody's contradicted us yet, that it is the world's only open source implementation of the ETSI LI standards. Being open source, it's actually reasonably low cost, and so it's quite, you know, smaller, medium-sized providers, you know, are quite keen on it, but it is fully modular and very high performance, and so there is theoretically at least no limits on how far it can be scaled. It's modern software, it works, it's Linux-based, it works in VMs, it supports vendor interception features, and these days we can say it's quite widely deployed and used. It's extensively deployed in New Zealand, but increasingly we're having users in a bunch of international jurisdictions. The architecture is like this. It closely follows the standards. There's a provisioner where the network operator will configure an intercept. It does have a web interface available if they want to use that. There are collectors that attach to the network and either intercept mirrored traffic or sent traffic from network components, and they do the encoding. And then the mediator supports the secure connection to the law enforcement agency, so all the information comes back through the mediator and it is sent to the LI. OpenLI, you know, we've been going 5 years now. I think it's purely IP based. It doesn't support conventional telephony traffic at all. It basically uses SIP and radius as the signaling. Currently, we support voice intercepts. We support full IP data intercepts. But as I think Jeff has said yesterday, you know, increasingly with encryption, that's becoming less and less useful. And we're working with a European provider to support email intercept. It has, since the beginning, had a very limited amount of mobile data support, but we really need to do better mobile support. So why mobile? Well, it really comes back to the data intercepts aren't that interesting. The most interesting intercepts are the voice intercepts, and it provides law enforcement often with the most information because, you know, people are pretty casual on the phone, and sometimes they talk a bit too much and things like that. And if you're doing voice intercepts, mobile is pretty much where it's at, right? There's some stats here that come out of the UK. They're quite good at gathering and publishing those stats, but I think that's pretty representative of the market worldwide. And certainly when we've talked to network operators, they tell us that vast majority of the intercepts that they get occur on their mobile, warrants for intercepts on their mobile networks. The other thing that's going on in the background is that we've had some really good support from ISOPHASIA, and we got a grant, supposed to do it all last year, but we're still going, called OpenLI for the Pacific Islands. Now, when we put this in, we did it in a little bit of hurry, and we possibly didn't have all the information we could have. So we said, well, the first phase is we're going to go out and we're going to find out all the requirements in the Pacific. And so we surveyed the legislation, and we went to the Pacific Island Telecommunications Association Business Expo in Port Moresby and talked to people. And I had this slide before, and in New Zealand and a lot of advanced countries have got pretty much to the end, and there's always new operators and things, you never completely finish. But it turns out that everybody in the Pacific Islands has stopped there, right? So when we looked at them, they all have legislation that enables them to do lawful interception or requires operators to assist the police in investigation, but none of them have gone beyond that point. None of them have regulations saying how they're actually going to do it, and none of the law enforcement agencies have gone on to the stage of starting to implement stuff and talking to network operators about how they're going to do things. But the other thing that came out, of course, is that we really need to improve our mobile. Mobile is hugely important in the Pacific, and all of the networks have, all of the islands, have some sort of mobile operator, or nearly they all have some sort of mobile network, and mostly they're at the 4G stage. There's a bit of historic stuff still around. They are looking at going to 5G, and with the fibre upgrades that are happening in the Pacific, that's increasingly making sense, at least in a technical sense. So we decided we really had to do some, and we had a big hint that we should be looking at 4G, but we thought we better review what our options were. So OpenLI is entirely IP-based. We have never supported traditional networking protocols, so it really didn't make sense to look at 2G or 3G, and in particular, the world is really moving on to them, even in the poorer parts of the world as they're being phased out. 4G is still really common. 5G in many senses builds on 4G protocols. Some of the names have changed, but often the underlying protocols are pretty similar. And in particular, the 4G standards are based on some of the standards that we've already implemented. Shane's going to talk a lot more about that in a minute. 5G is clearly where we want to end up. It's not useful in the Pacific yet, so using ISIF money that's intended for the Pacific is probably not an ideal thing to do. And realistically, if we're going to do 5G, we need to have pretty good 4G support anyway. So that's where we got to.
Thanks, Richard. Yes, so I am going to be talking a little bit in more detail about how we've had to update and think about changing the OpenLI software to accommodate the specific use case of mobile networks. So just to recap a little bit, I always like to think about these problems as a case of what outputs do I need to produce. And as Richard showed, we have two handovers that we need to provide to be a compliant interception solution. We need the HI2, which is the signaling handover, also known as intercept-related information. And then we have the HI3, which is the communication content. And the specific formatting and the transport and all of the details of how these handovers should operate are defined in this particular ETSI family of standards, the 102232 standards, and we implement quite a few of them already. But the thing about these standards is there's quite a few of them because the set of events and the set of metadata that you want to associate with a particular type of communication varies depending on that communication, right? So the events for an email interception would be different to the events for a voice interception, and mobile is no different. But when we started looking at 4G, an important component of a 4G network is the IMS, IP Multimedia Services. Now, this is a system within the mobile core that deals with those traditional telephony functions. So that covers all of your voice, it covers your SMS, it covers your MMS. They all happen in there. But because, as you can see from the name, this is essentially all IP, right? It's IP with SIP for the signaling and RTP for delivering the media, right? And this is used almost entirely extensively within 4G, VoLTE, and 5G networks. So here's a bit of a visual representation of where the IMS sort of fits into things. Hopefully the pointer works. There we go. There's our IMS. One thing I should note is that though I've sort of drawn the IMS here as a single logical entity, it's actually made up of a whole bunch of different services. So that you've got an SBC in there, you'll have a media gateway, you'll have user authentication databases, and so on. But what I want to highlight here is that we've got our person over here making their call over 4G, but it's basically SIP and RTP sort of all the way through. The only case where it's not really is when the IMS has to convert it to the old school telephone network if they happen to be calling somebody on a landline. But this is really great for us from an interception perspective because it means that it actually falls under a standard for voice over IP rather than one of the mobile standards, right? And OpenLI already supports the vast majority of what is in the ETSI 102.232-5 standard, which is the voice standard, right? So all we have to do at this point is add a few little extra bits and pieces in to cover some of those mobile-specific applications that have been added in later. And specifically, these are adding in location-related data and supporting SMS messaging. When it comes to mobile data itself, that gets a bit more complicated because that falls under the purview of the 3GPP folks, and they like to write very, very, very long documents. So the standard for mobile data interception is nearly 400 pages long, and it covers just about every type of mobile technology that has ever existed. And it's impossible for us, obviously, to go start at page 1 and implement the whole document. So we have clearly focused our attention on 4G and specifically the evolved packet services. So data connections within an EPS core are generally transported over GPRS tunnels, right? And those tunnels are managed by the GTPC protocol. And we can use that to map user identities to active tunnels that are shifting traffic around, which is a key part of interception, right? We need to be able to decide whose traffic or which traffic we need to intercept. The GTPC protocol is also a big source of our IRI, so our metadata events. There are two versions of GTPC protocol, but fortunately for us, once you get to 4G, it's all GTP v2. And then we have the GTPU protocol for actually shifting around the data, which is really just an IP wrapped inside of a header that has the GTP tunnel ID. Right, so if we've done a good job of parsing and recognizing user traffic in GTPC, then intercepting GTPU is just a matter of looking for the right tunnel IDs. One slight complicating factor in the mobile space is that there's not necessarily a single identity that a law enforcement agency may present you when they want you to undertake an intercept. So the standards allow them to specify any one of these three things, which is First one is the MSI SDN, basically the phone number. That's probably the most common one that they're going to use. But in theory, they could also ask for you to perform an intercept based on the IMSI, the SIM card unique identifier, or even the IMEI, the unique identifier for the phone hardware itself. But the good news is, as Richard mentioned, we've done a little bit of work in this space previously, supporting a 2G, 3G MVNO. So we've actually already got some code in place to recognize and parse the GTPC traffic. But their use case was a little weird in that they weren't interested in intercepting GTPU tunnels. They had assigned IP addresses, kind of like a radius sort of setup or a DHCP style setup to their users, and they wanted us to intercept the traffic that was using those IPs. So that's what we were doing in that case, and then we were producing the output as a UMTS interception. So just to recap, we've identified a few tasks that we need to complete to have mobile capabilities. Extend our VoIP interception to fully support what we can see in an IMS, intercept GTPU traffic based on tunnel IDs, make sure we cover all the possible identifiers, and also update the way that we encode intercepted traffic to conform to the standards for EPS networks, which means that we need to use EPS rather than UMTS. So where are we at? So SMS, done. I did it the other day. SMS support for any messages that are being transported over SIP, such as what you would see at an IMS. That's included in the most recent OpenLI release, pushed out last month. It also includes a particular feature that I want to highlight here just because it actually took more than half of the time to implement. Doing SMS itself was fine, but there is a very little edge case in the standards that say if the law enforcement only wants the IRI portion of the intercept, then you have to obscure the message content, which means you have to decode it, rewrite it all with like zeros or spaces, re-encode it, push it back out. That took most of the time. The rest was really easy. So we've done a bit of testing so far, but the number of examples we have has been a bit limited. So if anyone out there is willing to provide us with a few examples of some SMS traffic for us to confirm that we're doing well, that would be great. Location, this is also done for IMS intercepts. So we grab the p-access network info header out of the SIP traffic and plug it into the intercept records as a target location field and encode it as per a 3GPP information element. Right, so we've done some testing with this. We've confirmed the encoding is correct. So yeah, that's also in there and done. The GTPU is probably the biggest remaining task, but I'm really hopeful that we can reuse a lot of the code that we already have for parsing GTP. Again, our biggest problem is going to be getting some good examples to work with. So anyone that can help with that would be great. So that shouldn't take too long once we have those examples, probably done by the middle of this year. And then the identity stuff, that's a relatively simple task, and I'll probably be working on that as soon as I get back to New Zealand, so it should be done by the end of March. So where does that leave us longer term? So obviously we want to finish the 4G implementation within our ISIF grant period, so we've got a few more months to do that. But simultaneously we want to be trying to get a deployment or two up and running out there with users, because in our experience, every time we try to roll this out onto a new network, and every network is different, everyone does a little bit of custom bespoke things, or they use a vendor that we haven't seen before and that vendor decides to do custom and bespoke things. It introduces some things that we have to account for in our software. So in that regard, it's good for us to start that deployment and iterative process early, because anything that comes up during that process, we can probably justify spending time and energy working on that under our existing ICE of Asia grant. Now, ideally, we'd like to be doing this stuff in the Pacific, but we are more than happy to engage with other users in the wider APNIC region with the idea that this would contribute to an eventual rollout in the Pacific. After that, it becomes a matter of thinking about 5G, as Richard said. And in particular, that does become covered by 3GPP standards, and we need to sort of go back and see all of the sections that we need to do. We also, in particular, a big requirement that comes out of the 5G standards is these new interfaces, X1, X2, and X3. These are defined in ETSI 103.221, and these define a standardized way in which LI system components should communicate with one another or move intercept records between one another. And these are ways in which actually it allows vendor equipment to mirror or pass intercepted traffic into things like OpenLI collectors in a standardized way. So that's pretty much us. OpenLI is a project that sort of started from the network operator community and is designed to benefit the network operator community. It's designed to give operators a low-cost but completely functional option that they can use to meet their lawful intercept requirements. So we love to have your support or any assistance that you can give to help us keep the project going and keep making it better. And you can do that in a number of ways. You can try out the software and let us know what you think or what we need to improve on. You can provide traffic samples like I asked about, like I requested earlier. And you can, or just have a chat with us about things that you'd love to see in a project like this, things you'd like to see us do. And we can take all that on board and see where we go from there. So I believe that's us. Thank you. We can take questions if there's time.
Anurag Bhatia, Hurricane Electric. Thanks for the great slides. I understand your focus is on putting up a system and getting the software part working. But out of curiosity about the whole ecosystem, with so much of encryption happening, all the way from simple chat apps doing end-to-end encryption to even the wider web with the good projects like Let's Encrypt, how useful is the intercept data these days?
So that's a really good question, and from our perspective, because it's used in evidence in court, we can't change anything, so we don't do any decryption or anything like that. I think that's why we want to move into mobile and voice, because that's encrypted too, but then the operator has the keys and the law enforcement can ask for the keys and decrypt it. I suspect that data interception, particularly messaging services and things like that. There's all sorts of companies operating in the shadow. Maybe they provide a service. I don't know about that. I really can't tell you. Yeah, it's a great question. I don't have a definitive answer.
It may end up being a case of legislators trying to enforce their will on the service providers who provide those messaging services. We sort of go full circle back to having backdoors and things like that.
Let's hope not, but yeah.
Thank you.
All right, have we got any other questions for Richard or Shane or both? Any online? Okay, great. All right,
Thank you.
Guys. Okay, next up we have Anurag from HE to tell us about his work on a distributed latency monitoring. So please take it away. Look forward to it.
Thank you. Let me get the clicker working. Okay, this works. Good afternoon, everyone. My name is Anurag Bhatia. I am from Hurricane Electric. We operate a global backbone in 56 countries, hundreds of POPs. Essentially, today I'll be talking about distributed latency monitoring, tooling around monitoring latency at large scale, which is scalable. So it starts with the idea of looking for a smoke ping alternative. How many of you in the room have used or actively used smoke ping? Can you please raise hand? Okay, great. So for those who may not know, smoke ping essentially just monitors the latency, packet loss. It's one of the great old tools with which most of us have started plotting the latency numbers. It supports ICMP, HTTP, DNS, and bunch of other things based on the probes. So you use the respective probe against the target you want to monitor. It's easy to configure, and it can send email or alerts if there's a problem. Now, why look for alternate of smoke ping? There are a bunch of challenges with smoke ping. Essentially, challenges around it's hard to scale up. Why it's hard to scale up? It's because smoke ping essentially sits on a single server, single system, and if you need multiple locations, you need more and more smoke ping installations. They don't really club together. So as an example, if you got say something like 5 locations and you are trying to monitor 50 endpoints, you're going to watch out at 250 graphs. That's a lot of work to do. You cannot really watch out for 250 graphs on regular basis and expect to get anything useful out of it. There is no way of a federated view. So if you have 5 installations, you have to log in and access 5 of them individually. There's no way to have a single dashboard with all of them together unless you put some other workaround it. Out of box, there's no solution there. It has limited alerting support. It can alert you based on the emails, but then modern systems expect you to have alerts based on other push mechanisms, whether it's some sort of API call for pushing alerts on Slack or some similar system, or even opening a ticket using a REST API call. Why look for alternative? Again, it's important to watch out for latency. Overall, this is a requirement which stays for most of networks, all the way from small ones to medium to large ones. Ultimately, you will end up in monitoring latency from many sources to many destinations, and once you do it at that scale, it becomes hard to watch out for so many graphs. So you may want to have an aggregated view. It's easier to have a single tool for monitoring of latency, as well as everything else, including monitoring of servers utilization or router interface traffic, etc. Ideally, you may want to have such a system running in a high availability. In case of smoke ping, the only way to make it highly available is to just have multiple installations which do not speak to each other, operating absolutely independently, and then ultimately generating multiple alerts. But there are better ways around it. So introducing you to Prometheus. Can you please raise hand if you have used or actively used Prometheus? Okay, I see good show of hands, great. So Prometheus, it's a tool, in itself, it's just a tool, it's a time series database, it retrieves metrics. Everything in case of Prometheus is metrics. It essentially pulls metrics and stores them in a time series database, and it makes those metrics available. Now, once you pull the metrics, you can literally do anything based on that metrics. By default, it's based on a pull model. So Prometheus would go and pull metrics from various agents. These agents can be installed across different locations, and it can store metrics, and these metrics can have labels. So a CPU can be, a value can be a label, a destination can be a label, CPU or memory utilization, or even network traffic. Literally anything you can think of can have a number, can just be there sitting as a metric, and can be scrapped by Prometheus. It speaks to the agent by default via HTTP. So you can speak to agents over regular HTTP, or of course HTTPS, or an HTTP running over some sort of VPN tunnel. And you store them in a highly scalable time series database. Basic idea of the Prometheus design, if you have not used it, Prometheus sits in middle with the storage. It pulls the metrics from various set of exporters. Now, these exporters can be exporting anything. They could be exporting a system value. So there's a popular open source exporter called Node Exporter for getting various metrics out from a Linux server. You can have exporters for pulling latency data or DNS data. You can have exporters for pulling data out of, say, Docker Engine. You can have exporters pulling data out of even Ripetless at this point of time. It also supports push mechanism, but that's with a push gateway. That's essentially turning pull into push by having an extra exporter in between. Now, when you store all these metrics, this stays available and can be queried via an API call, or simply with popular tools like Grafana, which has these days become a de facto open source tool for graphing. It can pass this to an alert manager, which can send this as an alert. And it solves almost all the problems I just described in the smoke ping model. So the important thing to remember about Prometheus, everything is metrics. Whatever metrics you are grabbing, you can have a system to act on that. You can plot it, you can set alerts, or you can have systems to act on that. So this can be interpreted or graphed in any way. So going back to the previous example, 5 locations, 50 graphs, you can say, I want all the graphs of individual location on a single graph, or you can say, I just want a single graph with literally everything, with literally 250 graphs. It's completely flexible and up to you. You can do averaging on the data. So Prometheus supports quite nice computation on the collected metrics. You can say, show me data with only 1 minute averages, or show me data with 1 hour averages. Don't show me individual spikes if that's the use case. And you can attach any sort of label. So it's common for large systems to have a label, like you can say destination country HK as an example, or you can say destination type cloud. If you're monitoring, say, your latency towards various cloud providers, you can say destination type as downstream and start monitoring latency towards downstream. You push this via alert manager against a predefined rule set. So if this rule is violated, just send an alert, as simple as that. And because it's metric, the same system is used for latency or network traffic, or even just any other number which is being collected. Here's an example of metrics. I'm querying one of the server. I'm not sure if it's clearly visible on top with the color. Essentially, it's just a curl with the server host name, port 9100, where metrics are running, and it's just grabbing it out. And all this is simple text available over HTTP, super fast and super efficient to pull. Now, in order to monitor latency via Prometheus, there is a well-known and popular project called Blackbox Exporter. Since this talk is specific to latency monitoring, I'll be talking only about 2 of the exporters. Of course, there are hundreds of exporters, depending on various use cases. So Blackbox Exporter is an open source endpoint. It can trigger measurement, from various probes. It can measure HTTP, HTTPS resolutions, DNS, TCP, ICMP, and gRPC. It's written in Go, and it can be run as a container, or it's a simple Go binary. So it can simply be installed on various locations. As soon as you install it and configure it as a daemon, it will make the Blackbox exporter available over an HTTP endpoint. You can go and instruct it to run your measurements and reply you back with a simple HTTP call. Here's an example of a query. So this is a case where I am asking it to run ICMP v4. So it differentiates between IPv4 and IPv6 ping. So ICMP v4 for the target HKNOG. So essentially within the query, I'm providing it go and ping it and give me back the results. If you focus on the results, you will get an idea around. It gives you an idea around each of the labels. You see. Probe DNS lookup time, because we pinged an host name rather than an IP, it is showing us the resolution time it took for the DNS. And because this is in seconds, so this is essentially 163 milliseconds out there. Then it's giving you the overall probe duration, which seems to be 466 milliseconds. Time it took for individual ICMP phase for resolve, RTT, and setup. And of course, the hope limit, if there is something you need to monitor over time. and so on. And all this goes right in this example is just a query. It's not being stored anywhere. But essentially, when Prometheus does the same query, it would get these metrics and would store it in the time series database and make this available for easy plotting, which I'll show you in a minute. Another example, in this case, this is, instead of ICMP, this is a HTTP query. So it says HTTP 2XX, that's one of the probes. And essentially giving you the HTTP resolution related data on how you go and end up in resolving. So system is quite flexible because it's just metrics. You can literally store anything in there. And it's not a predefined hard-coded database which you can't change. You simply just add things and add labels as you need to. So if we follow it through, you will see something like, again, DNS lookup time, how much time it took for resolving DNS, the overall duration, and then various HTTP related part, including the connect, processing, TLS, and so on. So the protocol specific information as you would typically expect in such scenario. Now, here's a simple example of Prometheus configuration. You define this configuration in either a way where you define the target and then you add the labels, or if you are expecting multiple targets with same label, you can use this as well. It's a simple YAML interface, YAML style. You just define the domains you may want to monitor, the destination type, region, whatever suits you, which you want to use for grouping these graphs together at a later stage. Here's an example of Prometheus query. Now, this is a phase where we have already captured the data Prometheus has been capturing. It could be capturing it every minute, every second, every 10 seconds. It's up to the use case. It's quite flexible. Here's an example where we are saying, show us the probe ICMP duration seconds. So that's the ICMP probe. And in this case, I'm just matching the region named Hong Kong. This could be region named Hong Kong, or it could be just say destination type as cloud, and it would show for every region. Could be anything in that way. So you see all the data out there with all the labels. So you see destination type, instance, and all the information on the left side. And on the right side, you see the actual values which it has collected. Now, the Prometheus interface in itself is just for quick querying and debugging. It's not really used that much in production for generating graphs. Most of people use Prometheus along with Grafana. Grafana is where the graph and nice dashboards stay. For quick querying, this works really well. So another example, now this is slightly more specific. So instead of just asking it for region Hong Kong, I'm asking it for the phase RTT, and then also saying, don't give me data for anything else, just for this specific instance, which in this case is Hong Kong NOG's website, hknog.net. Again, you see the data here. Now, instead of only one reply, you see reply from essentially 5-6 destinations. These 5-6 destinations are different servers from where this essential ICMP ping happened. You see different host names in the job here, and you see the respective latency values based on where they were and the latency they found. Prometheus includes inbuilt graphing feature. So whatever you just saw, you can plot it right within Prometheus. But as I said, it's mostly for quick querying and quick lookup. It's not really used for permanent graphs by majority of people. So whatever can be queried, that can be graphed. Here's the case. Now, exact same query, and this is the case of Grafana. For those who may not be aware, Grafana is open source graphing tool. You can install it locally, run it locally, connect it to Prometheus. You provide Prometheus as one of the data sources to Grafana, and you put exact same query which we just saw in the Prometheus. So probe duration probe underscore ICMP underscore duration seconds, and then the respective labels. You can write these labels here, or if you're not familiar, you could even click on something like Builder, and that will give you a drop-down menu, so you can just go and select and easily build a query. Now, one thing interesting in this graph output is this 0, right? You don't expect latency to suddenly become 0. This is kind of case which you may want to avoid in a query. What it's essentially saying is probably for some reason the ICMP likely failed. So one can add that logic within this query. One can say, give me the values and exclude the values where it's 0, because you don't really expect latency to ever go 0 when these are far off locations. Here's another query, slightly changed. Again, data source remains Prometheus. In this case, instead of plotting it from all the locations, I have specified a specific host. This is one of my servers in Mumbai, and I just pointed it right there, and it's pulling data only from this server instead of pulling it from all the respective jobs. So whatever can be queried, it can be used to give alerts. So the same query which you saw in Prometheus earlier, you saw in Grafana, the same exact query can now be put in Alert Manager. This is an example of Alert Manager configuration. So here's a simple alert saying, if the latency to HKNO goes above 120 milliseconds, just throw an alert. And you can also put a rule like for, which says wait until it's that long. So wait for 5 minutes, as long as it's this much high for 5 minutes, then alert. This can be a logical number if you don't want to get too many alerts for slight spike, slight random spike. Again, same query out here, but in the end you see should be greater than 0.12. How you pick 0.12? That's because this is in seconds, so 0.12 essentially pointing to the 120 milliseconds there, and then just attaching the respective labels and severity as fits in. Here's another case which is from another server which is essentially far off from here. This server specifically is in Europe, so I've set a rule saying I expect latency maybe near or slightly lower than 300 milliseconds. So ignore if as long as latency is close to 300 milliseconds. If it's more than 300 milliseconds, just throw an alert. This is an example of email triggered by the Alert Manager. Now, Alert Manager in itself is a separate stateless application. So one can run Alert Manager in high availability. One can run Alert Manager as separate non-high availability setups. It's up to individual setup. If you run it in high availability, you can even do something like it can speak to 2 separate Prometheus instances and send you an alert by deduplicating. So if 2 instances are seeing a problem, it won't send you 2 alerts. It would just send you 1 alert. So how this scales up? There are multiple ways it scales up really nicely. You can distribute the monitoring endpoints. So now if you are, say, in 5 locations, you're not monitoring only from 1 location, and you're not having 5 complete software installation at 5 locations. You're just putting agent at 5 locations, a simple black box agent, which will simply export and does the measurement for you and give you the data. You can have multiple Prometheus server if this is something you need, if the availability is extremely important. And that same, and those multiple Prometheus servers can now go and query individual black box exporters, and both of them would just run absolutely independently while they will target against the same alert manager. And the advantage of such system is both Prometheus instances don't know that the other one is running. One can even go down. It just won't matter. And alert manager will always do the deduplication before sending the alerts. There is a support here for long-term retention on the S3 endpoint. So there are good projects like Thanos, again, open source projects like Thanos, which support exporting all these metrics out on a S3-like endpoint. So it gives you almost infinite scalability for storing these for as long as you really want. And besides Thanos, you also have projects like Cortex, or Grafana also has one of the projects called Grafana Mimir, which allows you to do that, if that is something you're looking for. Although personally I've seen, unless you're dealing with thousands and thousands of endpoints, typically scalability won't be such an issue. Another way it scales really well is you can also have hierarchical structure. You can have separate Prometheus installations all speaking to one single server with a federated view, and then have Grafana speak to that single server. So it can go from extremely simple to extremely complex and scalable setup. So how this all fits in? Here's an example for Thailand. So I put a couple of Thailand endpoints on an old school SmokePing instance. So this is a setup I have in Nuremberg in Germany, and here's a setup I have in Mumbai. I'm pinging these from the old school SmokePing. Again, as you see, you've got lots of graphs, lots of separate graphs with no federation in between. I can put these exactly on a single Grafana dashboard with individual locations. So this one again is from in case of this one is from Germany and this one is from Mumbai. I could have added these in a single graph as well. And if you need to view a specific graph, Grafana supports just by clicking and selecting that endpoint, and it will remove all other graphs. It will just highlight that specific chart. So you can literally have 50, 100, or even thousands of graphs within a single one, if that helps. Also, I'm using different averaging values here. So this one is a 5-minute average, while this one is a 1-hour average. So it supports this flexibility where you can have averaging of data if you need to, and whether or not you may want to see the spikes or just ignore the spikes in latency, short spikes in the latency. Now, this takes me to the last part. What about distributed? So we got system running, which is scalable, but ultimately it's still running within, say, your own locations, wherever you can have a server. You could even do it on a Raspberry Pi, wherever you are putting an agent. The last part on the distribution comes with RIPE Atlas. I hope you have heard about RIPE Atlas already by now with Leah's presentation earlier. For those who may not know, RIPE Atlas is a project from RIPE NCC, the RIR in the European region, and it's a distributed probe project where people host probe, these probe do the measurements, and it feeds it all back to RIPE Atlas. Overall, RIPE Atlas is a great project, but if you are trying to integrate it within your system, you may want to have something coming in the same setup, like a Grafana dashboard, which is pulling data from your own probes. You may want to have the same dashboard showing up RIPE Atlas data as well. So RIPE Atlas also has an exporter. Here's an example of using, so the name of the exporter is RIPE Atlas Exporter. I've linked it in the slides in the end. Here's an example of calling the RIPE Atlas Exporter. Essentially, I'm calling it on my server on the specific port where it's running, and then I'm providing it with the measurement ID of the measurement which I triggered on RIPE. You need to still go and create these measurements, but for most part, you may want to have a bunch of measurements towards your own network or towards interesting network preset at the RIPE end and collect those measurement IDs. Once you collect them, you can provide Prometheus with that and you get the data. So it is quite documented output. You see RIPE Atlas average latency. It gives you the AS number where it's running it from. It gives you the country code. In this case, it's AU, Australia, Germany, France, and so on. It gives you the destination address. Now, destination address is common in this case because we are essentially just collecting it against single destination for this measurement. You get the IP versions. So you'd expect typical IPv version 4, version 6, depending on the measurement. You would see longitude, latitude as the probes have it, the measurement ID, and the individual probe ID if you need that, and ultimately the values on the rightmost side for these measurements. So here's an example of the Prometheus configuration. So we are providing it with these targets. So for fun, I started looking at latency from various RIPE Atlas probe towards my home network. I just find it fascinating when packets are going all the way to space and coming back. So here's an example of one of the measurements, a public measurement running it towards my home IP. Here's a measurement running towards my server in Fremont, another measurement running towards my server in Germany. The rest of the part here is simply swapping the labels. You don't need to necessarily have a detailed idea of it, but broadly what it's doing is it is rewriting the labels so that it puts the correct labels when the Prometheus imports this metric from the exporter. You can get this configuration right in the documentation of Atlas Exporter itself. And here's how it looks. I've plotted all of the Starlink probes latency towards my my server in Germany, and you would simply see the AS number and the country name in the end. This is I just tweaked it because I did not necessarily wanted the source IP addresses. They would not make any sense. But source AS numbers and the source countries do make a lot more sense for this measurement. This gives you an idea if there is a spike or if there is something really odd. And as I said earlier, you could even average it out if you want to ignore individual spikes and are looking for long-term data when latency actually goes up or goes down. I think they have some sort of plan of routing within the satellites, right? That's what I heard in one of Mr. Jeff Houston's talks. So I'm curious how much of the change it will show on this graph once they enable that, where as of now, it's just going up to the satellite and beaming back. But once satellites start sharing within, likely the latency would change. Maybe good, maybe bad. We'll see how it shows up in the graph. Also, if you notice the lowest latency, if I select probably near to Germany or Germany, you'll find within Europe there will be lower latency as opposed to say US or some far off locations. So that is pretty much what you would expect because right now space is just being used in this case as a last mile. Summary, matrix world is becoming the standard for tooling. So it's a good idea to use that. If you are using old school SNMP monitoring, it might be a good idea to explore something like this. There are exporters for all sort of things. At my home, I have a MikroTik router and also do run an exporter for MikroTik, which calls MikroTik API and makes the metrics for MikroTik available. There are various exporters for use cases where there is no default exporter. These systems scale really well, and there are a good amount of support for the federation as well as object storage offload, as I said. And labels do play a very powerful part in clubbing these graphs together as you need it. All the references with the links to various exporters I just gave demo. There is also a SmokePing exporter if you want the old school SmokePing SmokePing like graph with the packet loss integrated right there. In case of black box exporter, it's not collecting the packet loss directly, but you can look for wherever it fails and run it more continuously to get that idea. So that's about it. Any questions? Do you have time for questions? Thank you.
I think Walt won by about a second.
I'll take my win, thanks. Hey, Walt Wolney from Hurricane Electric. Anurag, a very interesting presentation. I have one question and hopefully you can give me an answer. With Atlas probes, is it possible to map latency between networks in multiple regions? For example, maybe Hurricane Electric and level 3, for example.
Yeah, it would depend on where the probes are sitting and where the anchors are sitting because those are all well documented. So you can say something like to RIPE Atlas, pick all the probes on Hurricane's network and target the public addresses on the level 3 network. The challenge there would be there are not enough probes spread everywhere, so you might end up in having data only from say a couple of locations in US or maybe a couple of locations in Europe.
Yeah, the answer is yes. Thanks. Very good.
Thank you.
Hi there, Ed De Lange from InkZA. Not so much a question, but just a comment. Look, I use Prometheus and setup like yours works great. But just on the SmokePing thing, it does have a way to distribute the probes actually. We use it where we've got one centralized SmokePing with nodes sitting around our country, which works quite efficiently. And it does it a bit neater than Prometheus does, but I still prefer the Prometheus install.
Okay, thanks for the input. I think there are multiple versions for SmokePing now over time because a lot of people use the default one coming from the official source, but a lot of people also use the Linux server.io Docker containers for SmokePing, and there it gets trickier. So yeah, thanks. Yes.
Hi, this is Robert from the RIPE NCC, somewhat involved with Atlas. Thank you for this. This is awesome, especially the last part. I really like that. I think a lot of operators would be really, really happy if they could, with as few clicks as possible, actually use the exporter and say, okay, so for example, I have an anchor. It is measured. The system measures it for free. Here's the ID. Do the things. That would be lovely because it would make it really, really simple for the operators to join in and get free data and graphs and more understanding of how the world sees their networks. If we can work together on that, or if you're already almost there, maybe we can talk about it offline.
Okay, I can imagine something like a project on GitHub with all the code integrated right there. So it's simply you pull the code, you spin up containers, it spins up Prometheus, it spins up the exporters, it spins up literally everything, and you simply provide it with the measurement IDs. That's the only manual thing needed, and then it just plots all that for you. That would be the easiest start, where people start enjoying it and then start considering something like integrating it within existing system.
I think this is the beginning of a beautiful friendship.
Thank you.
Okay, any other questions? Any online? No. All right, thank you very much, Anurag. Okay, that's the end of this session, so we now have a break. Just some housekeeping for tomorrow. So the closing social will actually be off-site. To get there, all the information is on the Apricot website. It will be via public transport, so we'll be providing BTS and Metro tickets to attendees. They will be given out tomorrow. If you're unable to be here tomorrow to get the tickets before the social, please see the registration desk just for more information. Otherwise, we hope to see you there. I think it's at the Museum Siam. So it should be a good night. Thanks.